This is the main sequence of the HR diagram. This line right here, the red one that goes from lower right hand corner to upper left hand corner. And I think I have extensively discussed about different characteristics of this main sequence stars. And remember, we have talked that 90% of the stars are on this main sequence. Then we talked that the whole process that the stars, all these nuclear reactions that we have inside stars. So basically, when a star is on the main sequence, it will burn hydrogen into helium. So that will be the main reaction that they have. And so that is what most of these, almost all these main sequence stars are doing, right? And we talked that, and then how the life that they spend on the main sequence. The basic idea is depending on the initial mass that a particular star has, it will spend different periods on the main sequence, and also the other, other evolutionary tracks. Now, if you consider a low mass star like our sun, it will spend only it will take around 1 times 10 to the power 8 or 0.1 billion years to form the star. And after forming the star, and remember that we talk how stars can form, right? So that is under the topic of this interstellar matter or triggering star formation. And we talked that before this particular section. And once the particular star enters into the main sequence, it will spend some time on the main sequence by burning hydrogen into helium. And this is what we have been talking up to now. And after that, after a certain time, it will move on to a different phase, which means it will go out from the main sequence and will spend another 1 times 10 to the power 9 years in the phase called giant phase, and we will be talking about this today. And what you can observe on this graph is, if you look at these columns, when the mass, the initial mass of the star increases, the time it takes to form a star is decreasing, right? You can see that. And at the same time a particular star spends on the main sequence also decreasing. And so this is basically a decrease. That is the most important thing that you have to understand here. And the time it also spent on the giant phase also decrease significantly, right? So what this indicates is if your initial mass of a star is higher, the process or the evolutionary process is faster, right? So which means it forms quickly and it will spend only a very little time on the main sequence of the chart diagram, and then you move on to the giant phase and also spend a smaller time, right? So we have discussed about this before. And also I have here put some of these, the same information in a quite different way. That is how these stars spend their lives on the main sequence. You can see that this first column is the spectral class. We have discussed this before. When you go down, so that means you are go down with the temperature. So the temperature goes down with that spectral class. And then at the same time, you can see that the mass, initial mass, or the main sequence mass of the star goes down as well. And when the mass goes down, the time it spent in the main sequence is increasing, right? So the lower the mass, it will spend more time in the main sequence. right? So the mass is decreasing. Now all these, both the surface temperature and the mass, so they are actually decreasing. So they are decreasing, but once the mass is decreasing, the time they spend on the main sequence increases, right? So I think we have discussed all these things. Just go and look at these recorded videos if you can't remember. And so because of that, you can actually indicate or represent the main sequence as a mass sequence. What that means is when the star is on the main sequence, the more massive stars will be on this top left-hand corner. Right? It's like high mass stars. And these low mass stars are on the lower right-hand corner of the main sequence. And this is valid for all these main sequence stars. So that's a feature of stars. Right? And then we actually discussed furthermore about this main sequence stars. Then we discussed that, that what happens inside the main sequence is basically hydrogen burning into helium. Now, there is a question that what happens when the main sequence star runs out of its hydrogen. So answer to this take us along the next stage of the stellar evolution, right? In the main sequence, what will happen is these stars will burn hydrogen into helium. Right? So stars will remain on the main sequence until it runs out of hydrogen in its core. Right? So what that means is, if you look at this particular picture, in the core you have hydrogen and they are burning into helium, and at the end what we have at the core is just helium ash, because all the hydrogen now burned and converted into helium or helium ash. But however, you have the hydrogen burning shell just outside this core region, right? And then at the same time, in the most outer region, you have a non-burning envelope spell, and this is kind of the structure of the star at this particular point. Once it finished all these hydrogen at the core of the star, right? Now, this is the time the star starts to go outside of the main sequence. Right? Now, what happens is, now when you do not have anything to burn at the central region, so there is nothing to support for the gravity, right? So what happens is, then you have this hydrogen burning shell outside this core region. So this once the core heats up, this hydrogen burning shell will move towards the outward direction. Right? So this happens because due to high temperature. And when this goes to the outward direction, so what happens is the star will start to expand. So it will be expanded, and the size of the star will get much larger. Right? Because of that, you will have a higher surface area for this particular star. Right? And at the same time, what will happen is the surface temperature, which means the temperature of the surface of the star, will decrease, because once the star gets expanded, the distance to the surface from the central region will be larger, right? Because it gets expanded, and because of that, the surface temperature will decrease for the star, right? Now at this point, the star will be the size of the star is huge, and at the same time it has cooled down, right? Because the surface temperature has decreased. Now, when you have this type of a star, we call that as a red giant, right? So this is called the red giant phase. So that means the star has gone out from the main sequence due to this, due to the fact that it doesn't have any hydrogen at the core of the star. So all the hydrogen burned into helium. Now you have only helium ash at the central region. Now because of that, when the gravity contracts the star further, it gets heated up, and because of that heat, this outer shell with hydrogen, so it start to burn, right? Hydrogen shell burns, and the temperature also increases, and due to that reason, this outer part of the star get expanded, and because of that, the star get bigger and bigger, and this the distance to the surface of the star is increases from the central region, and because of that, the star will get cooled down, right? Especially the surface is cooler compared to the main sequence of stars, and because of that, the star will move into a different phase, which we called as red giant phase, and this particular image basically explains all these parts in this red giant phase. You can see that you have a helium-rich core, all the hydrogen is finished at the core, and then you have a hydrogen burning shell. This shell is the next layer that starts to burn hydrogen, and when it burns hydrogen, you know that when you burn hydrogen, you make helium. So all these helium that you made will come and falls into the central region, and at the same time, the volume of the star will increase, so it gets expanded, and because of that, this surface area, this surface right here, will have a lower temperature, because all the higher temperature material is at the central region, and once you are far away from that, you don't feel that temperature, right? So this outer surface will be cooled, right, compared to the central region of the star. And this is what we call as the red giant phase, and the size of the star will become huge at this particular phase, and that is what I have shown you here according to scale. And this is our sun, which is currently a normal main sequence star. And here is another star called L20. It's a giant star. And then this star called Cygni, which is a supergiant or the giant state. And you can see that it's in red in color, which is a cool down star, but the size is huge. And you can see this, how this the size different works, right? Now this particular table compares two stars. The sun is our main sequence star, and Betelgeuse is a giant or a supergiant star that belongs to the constellation Orion. Now, students who completed this task that I have assigned to you, one assignment for looking at 4 stars, should be very well familiar with this star now, Betelgeuse. You can see that the Betelgeuse is like 16 times more massive compared to the sun. So it's a huge star. And because of that, the size is also large, because it's a red giant, it's in the red giant phase. So its radius is larger and the size is larger. However, you can see the temperature is only 3600 Kelvin compared to the temperature of the sun. So which means these red giants are cool stars, right? But if you look at the luminosity, you can see that sun, of course, have one solar luminosity, and the Betelgeuse is 46,000 times luminous compared to the sun, right? You don't, even though Betelgeuse is so far away, this is why you can easily observe the Betelgeuse in the night sky, because it's a very luminous star, even though it's a very far away star, right? And if you have collected the data for that assignment, you probably should understand this now. And in terms of the amount of years, the age of the sun is just 4,500 million years. And for the Betelgeuse, just like 10 million years, right? It is this mass right here is responsible for this rapid evolutionary track that you have for the Betelgeuse. Right now, here is an example what would happen to us if sun becomes a supergiant. Now, as the main sequence is star, so as the main sequence is star, this is how our sun looks like. But when it becomes a supergiant, this will be the size of it. So you can, if you compare the size, roughly the diameter of this, our own sun will become 1 astronomical unit, right? And if you remember from the previous lectures, 1 astronomical unit means the average distance between our Earth and the sun. Right? Now, if the size of the sun becomes 1 astronomical unit, what will happen is this: the surface of the sun will touch our planet itself. Right? So we will not be able to survive at this point. So that is what will happen. And the only good thing is that you don't need to worry about this thing right now, because we have enough hydrogen inside our sun that burns into helium, and this process will go on for another 5 billion years, like approximately for 5 billion years. Now, this is why we are not worried about this too much. But if this is going to happen in, like, let's say within next 50 years, that means for sure we will not be able to live in this planet, right? But we know from our knowledge in physics and astronomy, by calculating like how fast these near-peer reactions happens, that we are safe for another 5 billion years. Sun has spent around 5 billion years on the main sequence up to now, and it will have another 5 billion years of time to spend on the main sequence. So until it leaves the main sequence, we are kind of safe. Right. Now here is the star called Betelgeuse. And if you remember now, this is a good point now to understand that everyone who observed should be familiar with this constellation, right? Now, unfortunately, if you are going to look at this constellation right now, it should not be visible on the night sky, right? For a reason. And if you go back and look at the previous notes, you should understand that different times of the year, you will see different types of constellations. At the time that I was assigning this to you around March, the constellation Orion was visible because it's a winter constellation and very clear right up in the sky. And this was why I assigned you this particular assignment. And if you have observed it, you can easily see these 3 stars, which we call as Orion belt. And at the same time, in one of the corners, this star is right here is what we call as Betelgeuse, and it is the brightest star that belongs to this particular constellation, right? Which is easily visible. And this image right here is actually the image of the Betelgeuse taken from Hubble Space Telescope. This should be an ultraviolet image as far as I remember. Yes. So it's an ultraviolet image taken from the Hubble Space Telescope. And actually, this image made the history because this is the first direct image ever made of the surface of another star. Right? Now, the only star that we knew up to this point was our own sun, right? And but this was the first time actually we have taken a direct image of the surface of another star outside the solar system, which is Betelgeuse. Right? So what I want to tell you here is just see the size of this star, depending on size of the star is right here, size of the Earth's orbit is this much. So it's a huge star, right? Now, now let's look at what happens in this red giant phase. Now we have discussed what happens when a star is on the main sequence. It basically burns hydrogen into helium in its core, and once you end up all the hydrogen in the core, the process that we discuss what happens after that, and it will move into this giant phase. Now when you are in this red giant phase, which is actually where the Betelgeuse star is right now, and
sir, we cannot see the shared screen, sir.
okay, so let me check what has happened. Yes, for some reason, sorry about that. Let me reshare the screen. For some reason, it has gone out. Can you see it now? Right, so let me reshare it. Can you see the screen right now? The shared screen?
Yes, sir.
Okay, thank you. Sorry about that. I didn't know that for some reason it has gone out. Right. So what I was actually explaining is, so maybe you probably have missed this slide. So let me explain. Right. So I was explaining actually this constellation right here, constellation Orion, that I have asked you to observe for one of those assignments. And here is the three stars that you will see as the Orion belt. So there is a specific name for that. And this is the star Betelgeuse. So Betelgeuse is the brightest star that you will observe in this constellation Orion, right? Now this image is the image of the Betelgeuse, which is taken from Hubble Space Telescope. And in fact, this is the first ever image that we made for the surface of another star, except our sun, right? So that's what I was talking about, right? Now, so let's look at what happens in this red giant phase, right? So remember that stars were in the main sequence initially. Now, when we move into the red giant stage, the central temperature of this star continues to increase, right? You know that we have now helium ash at the central region of the star, and that part will become, the temperature will increase in that part due to the fact that, you remember that I told you that there are only two basic forces that applies in this for these stars. One is the pressure and the other one is the gravity. Now, when you do not have anything at the center to create pressure, the gravity takes off, right? So which means you will have this, the star will start to contract and then increase the temperature at the central region. Now, when this happens, the temperature will increase, and this can actually go up to around 100 million Kelvin. Right now, you remember that you have now helium ash, right, at the central region. At the same time, so when the central region reaches to this much of temperature, like up to 100 million Kelvin, what happens is now, according to the nuclear fusion reactions, you have enough temperature to burn helium, right? You know that if you remember, or if you have learned a little bit about these fusion reactions, there are certain temperatures that you should have to fuse these lighter element into heavier elements, right? For example, you need to have certain temperature to burn hydrogen and turn them into helium. And that is what has happened when a star is on the main sequence. Now, once you have helium ash at the core, the star continues to increase its central temperature. And when this temperature reaches to 100 million Kelvin, then what will happen is you will have helium burning, right? Then you will have some helium that burns. So when you have this helium burning, actually, especially for low mass stars, this will be a kind of explosive event, right? So which means the helium will start to burn explosively, and this is actually called as a helium flash. So you will see it as a helium flash, right? Now, when you burn helium, what will happen is it will produce carbon and maybe some oxygen as well. Remember that this goes in an order, right? So first you have these lighter elements like hydrogen, and then it becomes helium, then helium becomes carbon and oxygen, right? So you can see that the star continues to make these heavier and heavier elements. And in fact, this is how you get these elements to the universe, right? So the first, this is the process of creating these elements basically. And so when you have this lower mass stars, what will happen is you will get this helium burning as helium flash, and this will make carbon in the core region of the star, right? Now, what happens is now the star will become relatively stable again when helium becomes carbon, right? And so there is something special that happens for these low mass stars. For the low mass stars, they have similar luminosities at this stage, which we call as the horizontal branch of the HR diagram. Now, this is what happens at that particular time. And actually, it is very easy to understand if you remember this graph right here, because it explains everything, right? Even though there are a lot of wording in the slides, they are to help you to understand what happens. But once you understand, you just need to remember this diagram. It basically explains everything. And here is the main sequence, right? And you know that high mass stars are in this region of the main sequence. And then low mass stars are in this region of the main sequence, right? And we have discussed what happens when a star is on the main sequence. The core region basically convert hydrogen into helium, and once you converted all the hydrogen into helium, the stars will move into this giant phase, right? Now you can see that this line has started somewhere here because I specifically want to talk about what happened to these low mass stars, right? So when a low mass star go into this giant phase, then for the low mass stars, when helium start to burn, you will have this thing called helium flash right here. And once helium is burned out, the stars will move along this path right here to this direction. And you can see that all these low mass stars, they kind of have the similar luminosities at this point. And this is why this particular part is called a horizontal branch, which means the stars will have a kind of similar luminosity. Right? So this axis is where you have the luminosity. If this the line is close to a horizontal line, so what I mean is this part right here. So that means you have the similar luminosities, which we called as horizontal branch of the HR diagram. And remember, this is only for low mass stars, right? Now, for the high mass stars, the process will be the high mass stars are in this region. So that process will be a bit different, right? Now, let's see inside the star what happens, right? So basically, I told you that there are helium inside the star. So what will happen is when you have helium, so when you have helium, so there is the nuclear reaction that would happen. So you have two helium alpha particles here. So alpha particle is basically helium nucleus, and they can combine together, right? If you have the correct temperature to make beryllium. But the problem with this reaction is this is a reversible reaction. And I mean, maybe students who are doing chemistry probably know better than me about this. And because of that, the beryllium is not a stable, right, nuclear. Because of that, it cannot survive, right? So this is why it doesn't make beryllium, right? So what will happen is, as the next step, when you have the beryllium, it will combine with another available helium nucleus. And once these two combine with each other, so what will happen is it will produce carbon. Now this is why helium becomes carbon, right? And then of course it will release gamma ray. And at the same time, another thing that can happen is once you have carbon, it can combine with another helium atom, helium nucleus to become oxygen, right? So that's why we have carbon and maybe a little bit of oxygen in this particular phase. And this process is actually have a specific name, and that is called as triple alpha process, right? Because you have three helium nuclei, so three alpha particles to combine together to make this process to work, right? Right. So this is what happens to a star when it goes out of the main sequence. And these last few slides that we discuss is what specifically happens for these low mass stars, not for the high mass stars, right? So what we are discussing here is we will basically discuss what happened to low mass stars separately, and then we'll come back again to see what happens to these high mass stars, because they are evolutionary, their endpoints are different, right? So they take two different paths depending on their masses, right? Now, if you look at this is again as an HR diagram, which shows you the tracks of the stars with different masses. Again, this is made to make it easy for you to understand this process, right? Now you can see that these low mass stars move away from the main sequence to different points. Something that you need to pay attention here is this number that you have 1.01 10 to the power 7, like that. So there is a number right here. That number is actually the number of years that each of these stars spends at different phases in their evolutionary process. Now, what you can identify is these high mass stars. You can see that this high mass star spends only relatively a smaller time in its evolutionary process up to a red giant or a red supergiant, while these low mass stars, they spend a huge amount of time, right, in each phase, right? You can see that these powers are 10 to the power 9 when you go down, but when you go up to these giant stars, it's only like 10 to the power 7, right? right? So this is what happens to these low mass stars. So that is one thing that I wanted to discuss with you. And then let's look at, so I'm going to stop this one, sharing. And this is the end point of what we have discussed last time. Now let's look at what happens after this process. So that will be right. That's over. And let me start this one and go as far as I can. So let me share what happens to these low mass stars after that particular process. Right, so I assume that all of you can see my screen, right? So I have shared the next presentation. So if you cannot see my presentation, then please let me know, right? Now this is what happens to these low mass stars after the red giant phase. Now you can see that each time when I am teaching, I have this particular diagram right here, which makes it easy for you to understand where I am at and what I am talking about. Now basically what we have finished talking about brown dwarfs. What I am doing here is I am just taking you in this path. So you have low mass star and it has become a red giant. And now I am going to talk about what happens after the red giant. So that will be the star will become a planetary nebula and a white dwarf at the end. Right? So that's what will happen for these low mass stars. Right. Now, after this burning helium into carbon, now once again for the low mass stars, that is when you have a stars with main sequence masses less than 8 solar masses, and this symbol right here represents the solar mass, they will never be able to burn carbon in their cores, right? Because you know that carbon is a bit heavier than hydrogen and helium. If you need to convert carbon into another heavy metal, you need even higher temperature. Right? Now these low mass stars do not have enough temperature at the central region to convert carbon into these heavier metals. Right? And because of that, we will refer all the stars that have main sequence mass less than 8 solar masses as low mass stars, right? And they cannot burn carbon into these heavier metals. And all these high mass stars that are this main sequence masses greater than 8 solar masses, they will be able to burn carbon on their other heavy elements, right? So they will take a different evolutionary path because of that. Now in this particular presentation, I will be talking about what happened to these low mass stars, right? Now for these low mass stars, so when helium fusion ceases of a low mass star, it leaves non-burning core of carbon ash. So which means you had helium burn into carbon, and now you have carbon ash at the central region of these low mass stars. Right? Now what happens is now you have carbon ash right at the center, and it is not burning because you do not have enough temperature. Now what will happen is this non-burning core will begin to collapse, right? Since it can no longer generate heat to balance its own gravity, right? So this is what always I used to tell. Once you do not have any fusion reactions going at the central region of the star, as in this case where you have carbon ash and it doesn't have enough temperature to make fusion reactions further to make heavy metals. So you have carbon ash and no fusion reactions going on now. The gravity, it's the attractive force, it actually wins at this time, which means it doesn't, the star doesn't generate enough heat at the central region to balance its own gravity. And because of that, the star will begins to collapse, right? Now, when the star start to collapse, then you know that it will lead to increase of the central temperature, right? When something is collapsing towards the central region, the center itself will increase its temperature, and this increase of the temperature will affect this outer helium shell, right? Remember that we are talking about the central region where you have carbon ash, but at the same time there is the helium shell outside there. When the central region temperature increases, what will happen is that increase of the temperature will affect to this helium shell, and once it came up to a certain temperature, the helium shell will start to burn, right? And at the same time, you have a hydrogen shell in the outer region as well, which will also keep burning, right? Now, at this particular level, what will happen is this outer envelope will start to expand to compensate for this. So while star gravity collapse the star in the central region, the helium shell will start to burn, and as a result of that, at the end, what will happen is this outer envelope of the star will expand, and as a result of that, we will have a different phase for now for these stars, which we call as supergiants, right? And this is how a supergiant looks like, right? So you have a carbon-oxygen core at the same center, mostly carbon, but you can have a little bit of oxygen as well. And then you have a huge helium fusion cell right here. And then you have the hydrogen fusion shell outside of that, right? And that is how a star looks like in this supergiant state. Right. Now there is a specific branch here in the HR diagram for these type of low mass stars, which we call as asymptotic giant branch, right? Now the reason is that when you have this the size increase of a supergiant star, remember that when this outer shell get expanded, the size of the star will become larger, and you know that for the luminosity of a star, there are two factors. One is temperature and the other one is luminosity, right? Now, you know that it is not the temperature that is important here, it is the surface area, right? Sorry, I think I got it correct. For the luminosity, there are two factors, the temperature and the surface area. And at this particular point where the star gets larger and larger, it increases the surface area, not the temperature, and because of that, the luminosity increases due to the surface area, increase of the surface area of the star, right? Now, what happens at this particular point is, due to this increase of the surface area, there will be a vertical rise on the HR diagram for these type of stars, which we call as asymptotic giant branch. Right? And at the same time, these supergiants will continue to burn hydrogen into helium shells outside the core, and see what happens. Now, these three graphs actually summarize this whole story. Right? If you did not, if you don't want to look at these wordings, just look at these graphs, and that explains basically everything that you need to know for this evolutionary process for these low mass stars. And as you see here, here is the main sequence that you have. And for the low mass stars, when it starts to burn helium into carbon, it will start this particular path and go into right here, where you have in this, the helium burning process, we call that as helium flash. That's what will happen. And then it will become, it will go into this particular point right here, where we talked this as a horizontal branch. Where you have the helium core right at this point, and then helium start to burn to become, to convert this to carbon, and this at this point. So I said that the outer surface area get expanded, and the size of the star will get larger. Therefore, you will have a higher surface area, and because of that, the luminosity or the brightness of the star will increase, and due to that fact, you will have an increase of the brightness like this. And this is what you call as the asymptotic giant branch, right? That means it quickly increases the luminosity. And finally, the star will be at this particular point. And at this point, what will happen is, you will have two distinct parts now for the star. So that will be, one part will be an expanding envelope. That is actually a relatively cool thin gases. And that's a separate part. And then you have a very dense core at the central region. And that is mainly consists of from carbon ash, right? So you have carbon ash at the central region. And apart from that, you have this expanding envelope, right? Remember that we talked right here that you have carbon ash at the center, and at the same time, the outer envelope of this target expands, right? Because of that, there are two distinctive parts now when the star is at this particular position. And because of that, you have these two distinctive parts are expanding envelope, and this is small dense core, right? And after that, what will happen is, and now this object that consists of these two parts, expanding envelope and this dense core, is called as a planetary nebula. Right? And these are just some of the examples of these planetary nebulas, where you have a dense core right here. And as the next phase, we will learn that this dense core is actually a white dwarf. So here are this few examples. And what will happen is actually, I guess the time is already 8 right here. And let me stop for right now, and I will take on the lecture from this point in the evening at 4 p.m. right? So that was what you have in the timetable here. So at 4 p.m. I will start from here and try to go as much as possible, right? Now, just pass the message to others as well who haven't joined. I know that there are around 30 students here. So they need to join for the lectures, right? Otherwise, I mean, you will be in a bit of trouble because some of you haven't completed even, you haven't done even these continuous assessments as well, right? So I will put another 2, and then we'll take the maximum marks of 2 of these assignments. And because of that, ask them to join for the lectures as well, right? So one of these assignments I will give probably within this week at some point. Anybody have any questions up to here? Right, so if not, let me stop right here, and we will meet again in the evening for the next section, right? So there are only like, we will meet only like 5 days, I guess, and we will finish out everything. So make sure that you join for all these lectures.